Hello, everyone, I'm Shutting. Welcome to our work, Primitive Generation and Semantic-related Alignment for Universal Zero-Shot Segmentation. This is a joint work by Zhejiang University and Nanyang Technological University. First, I introduce what is zero-shot segmentation. Zero-shot segmentation aims to segment not only seen classes that have been seen in training set but also unseen classes with additional semantic information. As shown in the figure, seen classes contain person, baseball bat, fence and so on that have appearing in the training set but unseen classes frisbee not appearing in the training set, but we need to segment it. As shown in the last row of figure, conventional methods can segment seen classes only, but with zero-shot methods, we can segment both seen and unseen classes. While previous methods are specifically designed for zero-shot semantic or instance segmentation, there are three different segmentation tasks including panoptic, instance, and semantic segmentation. The conventional method will design a model for each task, and there will be a total of 3 models. We found the common difficulties of these 3 tasks. One is a bias issue and the other one is a visual and semantic gap. Consequently, we tackle the above challenge and further design a unified model to address 3 tasks together and proposed our method padding. For the padding, we propose an primitive generator to synthesize visual features for unseen categories, which helps to address the bias issue and domain gap issue. Then, we introduce a collaborative relationship alignment and feature disentanglement learning approach to facilitate knowledge transfer. Firstly, let's talk about primitive cross-modal generation. We start by initializing a set of learnable primitives with the intention of capturing fine-grained information. The specific method involves feeding semantic embeddings and primitive groups into the network using transformer. Initially, we compute the similarity between the semantic embedding and the primitive group, selecting the primitive that is most relevant to the semantic embedding, and then adding Gaussian noise to it. This way, we obtain features composed of primitives and supervise them with actual visual features. Specifically, we use the maximum mean discrepancy, MMD, loss to narrow the gap between these generated visual embedding features and real ones. In summary, with the assistance of primitives, when given a semantic embedding as input, we can generate the corresponding visual embedding. Next, let's explore the impact of the number of primitives on the final results. We found that using 400 primitives yielded the most satisfactory results. Furthermore, we visualized the attention response maps of the primitives and discovered that they do capture fine-grained information. For example, in the first image, our 11th primitive primarily focuses on the cat's tail. The 206th primitive emphasizes the cat's outline, while the 324th primitive attends to the cat's ears. This observation supports the hypothesis that primitives can indeed represent fine-grained information. Next, we designed a module for relationship alignment and feature decoupling. For the generated unknown classes, we wanted to provide them with more useful supervision, such as the relationships between semantics. In other words, objects that are semantically close in the semantic space should also be close in the visual space and have similar distributions. However, conventional methods often directly transfer the relationships in the semantic space to the visual space using brute force. This approach does not effectively utilize semantic relationships because semantics and visuals do not naturally align with each other. Visual features contain more information, while semantic features can be seen as condensed information, meaning that there is redundant information in the visual features. Therefore, we considered decoupling the visual features before performing relationship alignment. The decoupling method involves separating the features into semantic relevant features and semantic irrelevant features. Then, we align the visual semantic relevant features with the semantic features. The semantic irrelevant features are expected to follow a normal distribution, representing features without specific information. On the other hand, the semantic relevant features should be able to be classified into specific semantic information through their features. To validate the effectiveness of our generation, we visualize the features of unknown classes generated by different generators. For baseline methods like the GMMN generator, the generated features appeared disorganized and lacked discernible intra-class and inter-class relationships. For the generator without alignment relationships, the primitive generator already achieved good results. However, the inter-class relationships were not very clear. By adding the relationship constraints, which we refer to as our padding module, we were able to generate features that were compact within classes and loosely separated between classes. Our padding achieves the state-of-the-art performance on the 3 segmentation tasks including panoptic segmentation, instance segmentation, and semantic segmentation. Our method obtains significant improvement over previous methods by up to 6%. For qualitative visualization results, we observe that our padding successively finds several unseen classes, for example, suitcase, grass, frisbee, road, tree, skateboard, that are missed or misclassified by the baseline model. Thank you for your listening. If you are interested in our work, you can visit our project page for more detailed information and come to our poster.